The pursuit of infinite energy stands as one of humanity's most audacious scientific quests, a challenge that brushes against the very limits of physics while igniting breakthroughs across every frontier of modern technology. As global energy demand continues to surge and the planet warms under the strain of fossil fuels, the need for abundant, clean, and sustainable energy has never been more urgent. True infinity may be beyond reach, bound by the first and second laws of thermodynamics. But recent scientific progress is bringing us closer than ever to energy sources so vast and enduring that, from our perspective, they are effectively limitless. Those laws remind us of our boundaries. Energy cannot be created or destroyed, only transformed, and entropy in closed systems always increases. They banish the dream of perpetual motion machines. No engine can run forever without fuel. Yet they also inspire something deeper, to search for sources so immense that for civilization they might as well be infinite. Across laboratories and observatories, from reactors that mimic the heart of stars to experiments probing the quantum vacuum, scientists are exploring realms where theory and engineering meet, and where the boundary between the impossible and the achievable begins to blur. Nowhere does this boundary glow brighter than in nuclear fusion, the process that powers the sun itself. Fusion promises virtually unlimited clean energy, our greatest hope, and our most elusive goal. At the center of that story stands ITER, the International Thermonuclear Experimental Reactor, a collaboration of 35 nations building the largest fusion device on Earth in Cataract, France. ITER's tokamak will confine a plasma of deuterium and tritium inside a perfect magnetic ring, seeking a self-heated state where the fusion burn sustains itself. Its target is breathtaking: 500 megawatts of fusion power from 50 megawatts of input heating, a tenfold gain known as Q equals 10. If achieved, it would dwarf the previous record, the joint European torus producing 16 megawatts with a Q of only 0.67, a giant leap toward bottling the power of stars. Construction has entered its most critical phase. At the core lies the central solenoid, a 3,000-ton magnet system, the beating heart of ITER. It forms an invisible electromagnetic cage to contain plasma at over 150 million degrees Celsius, 10 times hotter than the sun's core, while nearby components hover near absolute zero. In August 2025, ITER began final assembly of its reactor core. Westinghouse won a $168 million contract to weld 9 steel sectors, each about 400 tons, into the vacuum vessel. Every joint must align within a fraction of a millimeter. Precision engineering on a planetary scale. Despite delays in politics, first plasma is now projected for 2035. Across the Atlantic, another path proved ignition is possible. At the National Ignition Facility, 192 lasers converge on a tiny target, compressing it to stellar core conditions. On December 5, 2022, NIF achieved scientific break-even, 3.15 megajoules out from 2.05 megajoules in, a gain of 1.5, hailed as fusion's Wright brothers moment. Since then, NIF has repeated and surpassed success. 3.9 MJ in July 2023, then 5.2 MJ in February 2024, and an astonishing 8.6 MJ in April 2025. These were not one-off miracles, but repeatable ignitions, showing the physics is sound and reproducible. Yet triumphs reveal hard truths. NIF draws roughly 400 megajoules to power lasers that deliver about 2 megajoules to the target. Total system efficiency is far from net positive. And as research machines, neither NIF nor ITER converts fusion heat into electricity. That leap, turning raw fusion into usable power, still lies ahead. But one thing is decisive: fusion ignition works, and it can be done again and again. The promise is extraordinary. Fusion produces no greenhouse gases and only minimal radioactive waste compared with fission. Its fuels, deuterium from seawater and tritium bred from lithium, are abundant. A single liter of seawater contains deuterium with energy equal to hundreds of liters of gasoline. Fusion is inherently safe. If anything goes wrong, the reaction stops. No chain reaction to run away, no meltdown to fear. Still, enormous engineering and economic challenges remain. Materials must endure extreme heat and relentless neutron bombardment. Magnets, cryogenic systems, and plasma controls must perform with precision beyond today's norms. The learning curve is steep, but the trajectory is unmistakable. Private ventures and public labs are racing ahead, from Commonwealth Fusion Systems to Tokamak Energy and Helion, building smaller, faster, cheaper reactors. Some pursue pulsed magnetic confinement, others aim at direct energy conversion. Still others explore alternative fuels like deuterium helium-3 to reduce neutron load. Collectively, these efforts mark a new industrial era. Fusion not as a curiosity, but as a market that could power cities, spacecraft, and industries yet unimagined. In fusion, we glimpse a cosmic symmetry. The fire that gives the sun its life may one day sustain ours. At this threshold, our limits become catalysts for ingenuity. Now, look up. Far above clouds and weather, sunlight falls unbroken, clean, constant, and vast. That vision is space-based solar power, SBSP, a daring plan to harvest that light in orbit. The idea: place immense solar arrays in geostationary orbit, roughly 36,000 kilometers up, fixed over a single point on Earth. Bathed in sunlight 24 hours a day, these stations would convert power and beam it home as microwaves, or tightly steered laser light. On the ground, vast rectenna fields, lightweight mesh receivers, turn that radiation into usable electricity. The meshes let sunlight pass through, so crops could grow beneath, energy and agriculture coexisting. The advantages are staggering. Above the atmosphere, panels see up to 13 times more energy than on the ground, with no night, no clouds. That means steady, dispatchable power. Reliability comparable to fossil or nuclear, without the pollution. And the pieces are falling into place. Reusable rockets have slashed launch costs, making large-scale orbital construction plausible. Modular satellites could be assembled in orbit, expanding like scaffolds into kilometer-scale power stations. Ultralight photovoltaic films and radiation-hard materials push performance while surviving the harshness of space. Beam-steering electronics, phased arrays, aim microwave power with exquisite precision to the rectennas below. In 2023, Caltech's MAPLE experiment proved wireless power transfer in space and sent a detectable signal to Earth. The physics works. Safety is fundamental. Ground intensity would be comparable to standing in sunlight, a fraction of a household microwave oven. Each satellite could see a quarter of Earth's surface, dynamically rerouting power across continents in real time. In theory, energy harvested over daylight in Africa could power nighttime cities in Asia within seconds. Real obstacles remain: high upfront launch and assembly costs, international regulation and coordination, and debris mitigation in crowded orbits. But every great energy shift, coal, oil, nuclear, faced doubt at first. If we master orbital infrastructure, SBSP could deliver clean, continuous power at planetary scale. Beneath our feet lies another vast reservoir of energy, older than life itself, the heat of the Earth. Enhanced geothermal systems, or EGS, offer a revolutionary path to tap that constant internal fire. Unlike traditional geothermal plants that rely on rare natural reservoirs of hot water or steam, EGS creates its own. Engineers drill deep into hot, dry rock and inject pressurized water to open microscopic fractures, forming a network of artificial channels. Water pumped through this rock heats rapidly and returns to the surface as steam, spinning turbines. Then it is cooled and re-injected. Over 95% of the water is recycled, a closed, efficient loop. Temperatures at those depths can exceed 225 to 250 degrees Celsius, and deeper drilling, to 20 kilometers, can reach 500 degrees, hot enough to power industries directly. The U.S. Department of Energy's GeoVision study estimates EGS could provide 60 gigawatts of electricity by 2050 in the United States alone. Extrapolated globally, the potential climbs to 50 terawatts, 2.5 times all power humanity currently consumes. Unlike wind or solar, geothermal energy never sleeps. It delivers baseload power on demand. Adjusting water flow controls output instantly, making it an ideal replacement for natural gas peaker plants. After decades of promise, EGS is now crossing from experiment to reality. In 2024, Fervo Energy completed the first commercial-scale EGS project in the United States, a 3-megawatt pilot proving that engineered reservoirs can work reliably. The project drew on advances from the Department of Energy's Forge laboratory, where researchers refined stimulation techniques to boost productivity. Meanwhile, Quaise Energy is developing a radical millimeter-wave drilling system derived from fusion research, capable of vaporizing rock rather than grinding through it. If successful, it could bore 20 kilometers into the crust, reaching the super-hot rock that exists almost everywhere. At those temperatures, geothermal becomes truly universal, capable of repowering decommissioned fossil fuel plants using their existing turbines and grid connections. Economics are improving just as quickly. New multi-zone stimulation techniques can increase well output by 3 to 5 times while cutting costs in half. A 5-acre EGS site could deliver 30 to 50 megawatts, 10 times more than conventional systems of the same size. Once scaled, EGS could supply near limitless, dispatchable energy with minimal land use, no fuel imports, and a carbon footprint close to zero. If fusion and geothermal promise abundance from the stars and the Earth, another path looks inward, to the atom itself. Thorium-based nuclear power, especially in molten salt reactor designs, could deliver centuries of clean energy, while addressing safety and waste concerns that shadowed earlier nuclear eras. Thorium is not new. It was considered early in the atomic age, but its promise has sharpened with modern materials, controls, and modeling. Unlike uranium, thorium is 3 to 4 times more abundant in Earth's crust, with deposits spread across multiple continents. One U.S. Geological Survey estimate points to a single domestic deposit exceeding 64,000 metric tons, enough to serve national needs for generations. The principle is elegant. Thorium itself is not fissile, but with a captured neutron it becomes uranium-233, a fuel that sustains a chain reaction. In molten salt reactors, this fuel dissolves directly into hot fluoride salts that serve as both coolant and fuel medium. Because the system runs at atmospheric pressure, there's no risk of a catastrophic steam explosion. The salt's heat capacity enables very high operating temperatures, ideal for industrial heat and hydrogen, while remaining thermally stable. Liquid fuel allows continuous reprocessing, remove fission products while online, add fresh material, and keep the system balanced. In principle, a well-designed thorium MSR can achieve a breeding ratio above 1, producing more fuel than it consumes. This idea was put to the test decades ago. Between 1977 and 1982, the Shippingport Atomic Power Station ran a thorium-based light water breeder core, producing over 2 billion kilowatt-hours with a breeding ratio of 1.014, a self-sustaining cycle. Today, India leads thorium development with a 3-stage program: heavy water reactors, fast breeders, then advanced systems burning thorium-plutonium to close the thorium cycle. With vast thorium reserves and limited uranium, the strategy aims for secure, low-carbon energy for over 1,000 years. It's an audacious plan, pairing proven reactor platforms with fuel cycle innovation to unlock thorium at national scale. Still, serious challenges remain. Chief among them is protactinium-233, an intermediate that must be isolated from the salt before it decays to uranium-233, or it contaminates the loop. Industrial-scale protactinium separation is unproven. Researchers are testing extraction columns and electrochemical methods to close the cycle. Corrosion is another hurdle. The hot fluoride salts are chemically aggressive, demanding new alloys, coatings, and in-situ monitoring. Yet progress is accelerating worldwide. China, Russia, Japan, and the United States are investing heavily in MSR research programs. China is moving particularly fast, building experimental thorium MSRs to validate materials, operations, and breeding performance. If these efforts succeed, they could mark the rebirth of nuclear power, safe, flexible, and virtually inexhaustible, adding a powerful pillar to a clean energy future. If the atom holds one key to the future of energy, the simplest element may hold another. Hydrogen, lightest, most abundant, has long been called the fuel of the future, and for good reason. In a fuel cell, hydrogen meets oxygen and quietly makes electricity, heat, and pure water. No carbon, no smoke, just power. But hydrogen's greatest value isn't replacing electricity, it's storing and moving it across space and time. Think of the hard-to-electrify: steel and cement kilns, jet aircraft, deep-sea ships, heavy trucks. These demand dense, portable energy. Hydrogen can fire turbines, pair with captured CO2 to make synthetic jet and diesel, or feed solid oxide fuel cells with 50–60% efficiency, higher in combined heat and power. It can also serve as seasonal storage, bottling summer solar to heat homes and fuel industry in winter. Around the world, a hydrogen economy is forming. The United States targets 10 million metric tons per year by 2030, scaling to 50 million by 2050. The European Union, Japan, and South Korea echo similar ambitions, building markets, standards, and hubs for clean hydrogen. Color matters. Today's gray hydrogen from steam methane reforming emits CO2. Blue captures those emissions underground. Green comes from electrolysis powered by renewables. Electrolyzers split water into hydrogen and oxygen. Simple in principle, demanding in practice. Costs are falling fast. Next-gen PEM systems boost durability and efficiency, trimming both power use and maintenance. Solid oxide electrolyzers and fuel cells operate at high temperatures, unlocking exceptional efficiency and direct industrial heat integration. Infrastructure is rising. Dedicated pipelines moving hydrogen from ports and hubs to factories and power plants. Refueling stations are spreading for trucks, buses, and fleet vehicles, fast fills, long range, heavy payloads. Underground salt caverns offer massive, low-cost storage, gigawatt hours to terawatt hours, stabilizing grids through long, dark lulls. Hydrogen will not replace electricity. It complements it, becoming the flexible, storable glue that binds a renewable grid together. That is how we turn clean watts into reliable power, everywhere, anytime. Beyond the land, another untapped powerhouse churns at the edges of every continent: the oceans. Covering more than 70% of Earth, they absorb sunlight, wind, and the pull of the moon, harboring a constant, predictable source of energy. Tidal stream turbines tap the steady flow of currents, spinning generators much like underwater wind farms. Unlike wind or solar, tides rise and fall like clockwork, perfectly predictable centuries in advance. In Scotland's Pentland Firth, the Magen project's 4 turbines have already generated over 51 gigawatt hours, power for 6,000 homes. Globally, tidal stream potential could reach 150 to 800 terawatt hours per year, enough to meet national-scale demand. Wave energy is more complex but equally promising, turning the ocean's rolling rhythm into electricity. Designs range from oscillating buoys and point absorbers to submerged pressure systems, each capturing motion in a different way. Ocean thermal energy conversion uses warm surface water and cold deep water to run a gentle heat engine, continuous in tropical seas. Together, waves and OTEC could deliver steady, renewable power to island nations and coastal cities now reliant on imported diesel. Challenges are formidable. Saltwater corrodes, waves batter, and sensitive marine ecosystems demand protection. Engineering is catching up. Modular turbines and duplex stainless or composite materials are extending lifetimes and cutting costs. Smart mooring and monitoring systems stabilize devices, reduce maintenance, and safeguard wildlife in dynamic seas. Linked with floating solar and offshore wind, ocean energy could turn coastlines into living power plants, resilient, clean, and constant. Perhaps the most elegant energy idea is borrowed from nature itself: artificial photosynthesis. For billions of years, plants have turned sunlight, water, and carbon dioxide into chemical fuel with quiet perfection. If we could replicate that process synthetically, we could tackle energy scarcity and carbon emissions in a single stroke. The principle sounds simple. Use sunlight to split water into hydrogen and oxygen, then combine captured CO2 to synthesize liquid fuels, methanol, ethanol, or hydrocarbons. The reality is harder. Natural photosynthesis runs under 1% efficiency, with self-repairing enzymes and complex pathways we don't yet match. Industrializing it demands catalysts that perform multi-step reactions under mild conditions, efficiently, selectively, and without degrading. Still, breakthroughs are arriving. In August 2025, a University of Basel team reported a 5-part artificial photosynthetic system that stores both positive and negative charges under low-intensity light. It can accumulate enough energy for sustained reactions without high-power lasers or intense sunlight. Yields remain small, but the step is crucial, closer to true sun-to-fuel conversion. Imagine a closed carbon cycle, fuels made from air and light, releasing no net CO2. Every ton of CO2 from aircraft, ships, or power plants recaptured, then reused to make new fuel. No more fossil extraction, instead a perpetual recycling of sunlight into motion. One day, even the internal combustion engine could be carbon neutral rather than obsolete. Artificial photosynthesis may not yet light our cities, but it points to energy independence profound enough to reshape our bond with nature. For all our advances in engineering, the strangest possibilities still live at the edge of physics, the quantum realm. Here, even nothing is restless. The vacuum seethes with zero-point energy, tiny fluctuations that never quite vanish. Every mode of the electromagnetic field carries a half quantum of energy. Add up all modes and, in theory, the total diverges. This invisible sea reveals itself in real forces. In 1948, Hendrik Casimir predicted an attraction between two ultra-close metal plates. The gap excludes some vacuum modes, creating a pressure difference that gently pushes the plates together. Decades of precision measurements confirmed it. Emptiness is not empty. Can we tap zero-point energy for power? Mainstream physics says no. The ground state is already the lowest rung. With no lower level to fall to, there's no gradient to do work without violating thermodynamics. Yet vacuum energy echoes through the cosmos. It likely contributes to dark energy, the pressure driving the universe's accelerated expansion. But theory and observation clash. Quantum calculations overshoot the measured vacuum energy by 10^120, a staggering vacuum catastrophe. Another frontier, quantum energy teleportation. Through entanglement, a measurement here can change the energy bookkeeping there. It isn't faster than light, and it isn't practical power transfer. The energies are vanishingly small. Still, it shows the vacuum is an active medium, not static nothingness. Then there is antimatter, the ultimate energy density. Matter meets antimatter and annihilates into pure energy, E equals mc squared. 1 kilogram of perfect annihilation would release about 9 x 16 joules, over 20 kilotons of TNT. By any measure, it is the most potent reaction we know, but reality bites. Antimatter does not exist in bulk. We must manufacture it in accelerators and trap it with magnetic fields. Production is astonishingly inefficient,
only a tiny fraction of the invested energy is ever recovered, so costs soar and outputs stay microscopic. For now, antimatter remains a symbol more than a solution, a reminder that nature's fiercest powers often sit just beyond practical reach.
Between the stars and the quantum vacuum, we return to a simple question. How close to abundance can engineering take us? The final piece may not be generation at all, but storage, the quiet hinge that turns intermittent power into reliability. Lithium-ion unlock the clean energy era, shrinking from phones to cars to containerized grid batteries across cities and deserts. But limits remain: lithium supply, safety, and energy density. So researchers are building the next wave of storage technologies. Sodium-ion swaps scarce lithium for abundant sodium, cheaper, safer, and steady in cold climates for grid applications. Flow batteries store energy in tanks of liquid electrolytes, delivering 20-plus years of cycling with simple upkeep. Their superpower is scalability. Power and energy are decoupled. Capacity grows by adding bigger tanks, not new stacks. Iron-air systems rust and unrust iron to store energy, trading density for ultra-low cost and 12 to 100-hour durations. When winds lull and skies darken for days, these long-duration stores can keep whole regions powered through the gap. Beyond them, solid-state batteries promise higher energy density and inherent safety with non-flammable ceramic electrolytes. Costs remain high, but pilot lines are advancing, pushing solid-state from prototypes toward early mass production. Storage turns a solar-powered world into a dependable one, consistent, dispatchable, and resilient across seasons and storms. Every leap in storage multiplies the value of every clean watt we make, the hinge on which the transition swings. Step back and take in the full picture. From the heart of the sun to the depths of the earth, from quantum fields to ocean tides, a spectrum of new energy possibilities is opening. Fusion ignition has been achieved and repeated, turning starfire from theory into repeatable experiment. Space-based solar has beamed power across the void, proving wireless energy transfer in orbit. Geothermal reservoirs are being engineered where none existed, turning hot, dry rock into 24/7 baseload power. Artificial photosynthesis is starting to turn sunlight directly into storable fuels, closing the carbon loop. Thorium reactors are being revived, hydrogen networks are expanding, and industry is gearing up for clean heat and fuel. Storage technologies, batteries, flow systems, and long-duration solutions are converging to bind the grid together. For the first time, every major pathway to clean abundance is active at once. Not fantasy, but engineering reality. None alone grants infinite energy, yet together they promise freedom from scarcity and progress without end. Power as clean and universal as air and sunlight. Such a future will not arrive by chance. It is built deliberately. One breakthrough, one policy, one bold decision at a time. It demands relentless research, sustained investment, and political will on a planetary scale. Not only scientists and engineers, but visionaries and citizens who see energy as purpose, not just technology. Every reactor built, every solar array launched, every battery installed moves us from fear of shortage to confidence in abundance. We stand at a threshold as profound as fire, or the dawn of industry, with tools to rewrite the story of power. The next revolutions won't be measured in horsepower or kilowatts, but in what we choose to do with power that no longer pollutes, divides, or depletes. It will redefine economies, reshape nations, and one day carry us beyond Earth, fueled by the same cosmic fire that lights the stars. The quest for infinite energy is, in truth, the quest for infinite possibility. Though physics denies eternity, it grants us something just as extraordinary, a universe vast enough to keep us striving forever. So what do you think? Which breakthrough will change everything? Fusion, geothermal, space solar, hydrogen, or artificial photosynthesis? Tell us below. And if you're ready for more frontiers, subscribe and join us. The search isn't just about power. It's about our place in the cosmos and the limitless potential of the human mind.